Now, I am delighted to introduce our speaker today, Jianke Yang. Jianke is a fourth-year PhD candidate at UC San Diego Department of CSE, advised by Professor Rose Yu. His research interests lie in AI for scientific discovery, generative AI, and geometric deep learning. Recently, Jianke has focused on developing machine learning methods for uncovering governing laws in physical sciences and incorporating these discoveries as flexible inductive biases into predictive models. His work has been presented at leading ML conferences such as ICML and NeurIPS, and he's also been featured in Quanta magazine. Today, Jianke will be giving a talk titled Towards AI Co-Scientist, Automating Governing Law Discovery for Physical Sciences. So please join me in giving a warm welcome to our speaker today. And Jianke, without further ado, I am going to hand it over to you.
Yeah, thank you, Daniel, for the introduction, and thank you everyone for being here. I'm going to start sharing my screen. Let me know if you can see it.
I can see your screen, so
okay.
You're good.
Okay, perfect. So yeah, I'll get started. Today, my talk will be about Towards AI Co-Scientist, Automatic Governing Law Discovery for Physical Sciences. So to start with, we note that in recent years, AI has fundamentally reshaped how we approach scientific discovery process in multiple disciplines. For example, we all know that DeepMind's AlphaFold 2 has revolutionized protein structure prediction, accelerating the entire field of structural biology. And also in physics and applied mathematics, symbolic regression approaches like sparse regression and genetic programming have rediscovered classic equations of dynamical systems directly from data. And also on the right-hand side, more recent works also show how generative models can be used to generate atom types and positions in crystal lattices to explore entirely new materials and chemical compounds. And these examples highlight a growing theme that AI is no longer just making numerical predictions, and it is increasingly discovering the governing laws and understanding the mechanisms lying under the physical data themselves. And to understand this process, let's look at the typical pipeline of AI-driven scientific discovery. And I summarize it into 4 stages. That is problem specification, data acquisition, hypothesis generation, and finally, experiment design and evaluation. And more specifically, we will look into the stages where my previous work mostly focused on. The first stage of scientific discovery is always problem specification, where we as researchers clearly define the goals of discovery, formalize the setup mathematically, and bring in prior domain knowledge when necessary. And this sets up the stage for AI models. And as for the next data acquisition phase, we mostly use the typical setup in supervised machine learning, where we have a pre-collected data set for training. But yeah, this is for the data acquisition. And then next, depending on which problems we want to solve, we can use different techniques developed in the AI field to generate hypotheses. And examples of this include using language models for reasoning, which is the increasingly popular trend nowadays. And also other examples include numerical optimization of some symbolic models, which is particularly common for symbolic discovery, and also other general generative models for different tasks, such as generating molecules or crystals. And my research up to now precisely focuses on this interface to develop AI models that generate scientific hypotheses based on specific problems. And yeah, finally, we perform experiment design and evaluation, verifying these hypotheses against reality. And finally, we perform this process iteratively to refine the generated hypothesis until we find the satisfying one to describe the data well enough. And as we have mentioned, there are many domains in AI for scientific discovery, and unfortunately, I haven't got a chance to study every one of them. So more particularly, I summarize my research as discovering the governing laws or the symbolic equations that describe some properties of the dataset. This is, I think, broader than the most specific case of symbolic regression, where we just look at a symbolic expression, y equals f of x. So we are additionally interested in, for example, differential equations that describe how physical systems evolve in time or space. And for example, symmetries that tell us when a function is invariant or equivariant to certain transformations, or conservation laws that indicate that some physical quantities do not change over time. These are These are the things physicists often try to find from the observations, and we also want to make AI models work toward this end. And in this talk, I will cover 3 of our previous papers. So the first and second would be about symmetry discovery. We developed 2 models called ligand and LaLigand, short for latent ligand, to discover linear and nonlinear symmetry, respectively. And in the third part, I will discuss how to use these discover symmetry to inform equation discovery in dynamical systems. So we'll start with the first one, ligand, for discovering linear symmetry. Symmetry has proved to be a very important inductive bias in deep learning, and we can enumerate many examples for that. For example, we have Lorentz invariant networks for predicting particle jets property, and we have AlphaFold 2, which uses the SE3 equivariant network to predict the molecular structure. And more generally, these inductive biases can also be incorporated into generic architectures, such as graph neural networks, shown on the right-hand side, to be applied to many different tasks. But all of these equivariant symmetry-based networks has a common problem or feature, depending on how you view it, is that they require non-symmetry as a prior. So in other words, if we do not know the symmetry of a task beforehand, we cannot construct these equivariant models and ensure that they are perfectly correct in the corresponding scenario. Therefore, starting from this, we start to think about the possibility of developing a model that automatically discovers symmetry from data, rather than relying on fixed inductive biases to make predictions. And also, beyond the improvement of these equivariant or symmetry-based neural networks, we believe that the idea of symmetry discovery also has great significance in the application of machine learning in physical world, because symmetry lies at the core of modern physics study, and it is related to many physical properties by established theorems. For example, we have this Noether's theorem stating that every continuous symmetry of the action of a physical system with conservative forces has a corresponding conservation law. So we want to, from symmetry discovery, we want to build toward a prototype of AI scientist where it can, for example, start from identifying unknown symmetries and then build flexible inductive biases into these symmetry-based neural networks. And also, on the top of that, we can also generate novel hypotheses and eventually discover new physical laws, which would be of much more significance. So let's delve into introduce our method for symmetry discovery. But before that, I want to first introduce you to the mathematical concept of symmetry with rigorous math language. So we often use the mathematical structure of a group to describe symmetry. So basically, group is just a set equipped with an operation satisfying some group axioms, including associativity, meaning that if we have 3 group elements, G1, G2, and G3, and operate them together by the operator, then it does not matter whether we perform G1 times G2 first or G2 times G3 first. And identity element, meaning that the set must have an element which, if you operate it, if you combine it with any other element, it will yield the same result. And also, after we have the identity element, we require that each element in the group has an inverse element. So if you combine these 2 inverses together, they will obtain the identity element itself. And after we define the group, we can define the notion of invariance and equivariance of a function. So basically, if we have a function f and the group g, we call the function f g invariant if f of gx equals f of x for any input x and any group element g. This is saying that if we apply the group transformation on the input x, the output of the function does not change at all, meaning that it is invariant. And similarly, we have the notion of G equivariance, f of gx equals g of fx. This means that if we have the group element G transforming the input x, the output f of x will be transformed in the same way. And to look at a more concrete example, we can consider this function f on the 2D space, which basically multiplies the second component by 2. And we can see that this function is equivariant to the rotation transformations represented in this rotation matrix rho G. This means that, like, if we first apply f, that is to multiply the second component by 2, and then rotate it by any degree, the result will be the same as rotating by the same degrees first and applying the f or scaling up the second component by 2. And after we define the notion of symmetry, we then define our problem of symmetry discovery. So basically, we are given the data set of input and output pairs, x and y, of an unknown function. And our goal is to learn a symmetry group, capital G, and its action on data. And so there are 2 things we want to discover here. The first one is the structure of the G itself. And the second one is its more concrete action or transformations on data denoted by the rho y and rho x here. Here, the formula means that rho yg is a transformation on the output space y, and the rho xg is the transformation on the input space x, and they act on the data points y and x respectively. But how do we do this? We start from a probabilistic perspective. So we have this intuition that symmetry changes the data distribution minimally. More particularly, if we have the original data distribution denoted PD here, and we have a symmetry group where we randomly sample group elements, we can obtain a transform distribution denoted PT here. And we're saying that if the group elements are indeed the symmetry of the system, then PD should be approximately equal to P of T. So for example, here we show an example of MNIST digit classification, and the original data distribution is just the joint distribution of the digit images and the class label, which is an integer. And if we just ignore the similarity between 6 and 9 and roughly claim that SE2 containing all the rotations and translations is the symmetry group of the system, and then we apply random transformations from this group, we'll see that the resulting transform distribution containing the transformed digit images and the same class label would be approximately the same as the original data distribution. So how does this intuition help us? This essentially transforms symmetry discovery from discovering an abstract mathematical object to a typical distributional matching problem in generative modeling. So we use a generative model called GAN, which I assume many people in this room would be familiar with. So we have this generative adversarial network where we have two modules. So first, the generator, the task for the generator is to transform the data by symmetry transformation. And the discriminator aims to distinguish between the original and the transformed data distributions. And first, we take a closer look at the generator. So we use the capital letter phi here for notation in order to distinguish it from the group capital G. And the task for the generator is to generate a transformed data distribution that resembles the original data distribution. To do this, it takes in the original data point containing both the input and the output, that is x and y, and transforms it by a group element G. And since we want to learn the entire symmetry group rather than individual group elements, we do not select a fixed group element here, but instead we sample from a distribution mu over the entire hypothesis space of group elements. And then we apply the sample group element, or more precisely, the actions of these group elements on x and y respectively. This becomes a sample from the transformed distribution that the generator generates. But there is one more thing to consider here. So the distribution mu here is over the space of all the group elements, or a Lie group in mathematical terms, instead of a standard vector space that we most commonly deal with. Therefore, the next key design of our method involves how to model this distribution of the group elements. So yeah, this is highlighted in the red box in the visualization. So to do this, we make use of a result in Lie theory. And roughly speaking, we have a vector space that is the fractor G here, which is known as the Lie algebra of a Lie group. And we can obtain the elements in the group by taking an element in the vector space in the Lie algebra and apply an exponential map on them. The exponential maps for vectors and matrices can be computed differentiably. So therefore, to model a distribution on a Lie group that is the distribution mu here, we just have to define another distribution on the Lie algebra vector space that is gamma over the W vector and push it forward by the exponential map. And in practice, we just choose some common distributions in the vector space like Gaussian distribution. So just a disclaimer that this is just a very rough description about the math happening here. And I will be happy to explain more later if people are interested. But for now, I will proceed to talk about the remainder of our design and the experiment results. And finally, if we combine all of these modules together, we have the following training objective, which is pretty much similar to the original GAN formulation. So basically, we have two terms in the loss function. The first term, log d of xy, tells the discriminator to distinguish between the real and fake data points. And in this case, the real just means the original data points, and the fake just means the transformed data points generated by the generator. And then the second part of the loss function, which also involves the generator phi, tells the generator to generate the data samples that resemble the original data samples, so that it can fool the discriminator by generating such similar data distributions. And we train under this objective, and by this adversarial training, the generator is expected to obtain a similar transformed data distribution as the original data distribution. And yeah, putting it all together, we have introduced how we designed the symmetry generator, how we specifically model this distribution on a Lie group in order for the generator to work, and putting it together, the overall training objective of our method, GAN. So note that we start this from the intuition that symmetry changes the data distribution minimally, but we have never justified that that intuition is correct. But we do show some results in our paper about the correctness of this distribution, of this intuition. So first, we have this strong theorem saying that symmetry is the global minimum that allows the transformed data distribution to be exactly the same as the original data distribution under some strong conditions, which is this PD GX0 proportional to something, basically saying that the original data distribution is somewhat uniform. But of course, these strong conditions do not ever hold every time in practice. So we also have a relaxed theorem saying that symmetry leads to a lower generator loss than non-symmetry under a much weaker set of conditions. And this guarantees that our method can work in most practical scenarios. And yeah, so now let's look at some results, some symmetry that we managed to discover with this method. So we first look at a particle physics example, and here the task is called top tagging. Basically, it's binary classification between the top quark jets and the background signals from those crazy high energy colliders that physicists work on. And the input of this task is the four momentums of the particle jets. So the entire input is denoted the capital X here, and it contains multiple components, and each component is the four momentum of the particle jet. It is an extension to the regular three momentum in classical mechanics to relativistic scenarios. So basically, we have the second to fourth components corresponding to the regular momentum components, and the first energy components, which is additional. And the discovery of our model is the approximate restricted Lorentz group symmetry, which matches the ground truth Lorentz group symmetry in relativistic physics. More concretely, we can look at these representations discovered by our method. And the red boxes here denote the symmetry generator for those temporal boost transformation. And the blue boxes here highlight the rotation transformations in 3D along three different axes. And also, we can, after we obtain this symmetry generator set, we can compute the invariant metric of the system. And we were glad to find that this computed invariant metric from these symmetry generators is close to the ground truth Minkowski metric in relativistic physics. And this is a visualization showing how our discovered symmetry acts on the data. So here we visualize several marginal distributions, and we highlight a random portion of the data points. So we can see that while the overall marginal distributions remain similar, these individual data points are indeed non-trivially transformed to a new location from left to right, indicating that we managed to find non-trivial but also correct symmetry transformations of this data set. And also, one thing we noted in the beginning is that after discovering symmetry, we can use it in downstream tasks to improve the performance of equivariant neural networks. So here we consider one of these examples. So we actually use this discovered symmetry to do binary classification between the quark jets and the background signals. And we found that our discovered symmetry, which is highlighted as the Lee GNN model here, is only very slightly behind the Lorentz net, which uses the ground truth symmetry, but it is better than Lorentz net without any symmetry, or EGNN, which is a model with entirely wrong symmetry. And this shows the usefulness of our discovered symmetry. And next, I will quickly go through the extension of our first work called latent ligand, that is discovering nonlinear symmetry. So one problem with our previous approach, ligand, is that it transforms the data simply by matrix multiplication. But this is not always possible, especially in the following scenarios. For example, if we have the data points in the higher dimension, like this snapshot of a PDE system, which is an image of 100 by 100 pixels. And also, we have the nonlinearity issue. So for example, for some nonlinear dynamical systems, even though the phase space is low dimensional, the symmetry transformations on these low dimensional spaces can still be nonlinear and not representable by simple matrix multiplications. So how do we deal with these cases? So fortunately, we come up with this method. So we decompose the nonlinear group action either on high dimensional space or on low dimensional but nonlinear spaces into 3 parts. That is an encoder plus a linear representation plus a decoder. And the encoder and decoder just form an autoencoder network that maps the data from the input space to a latent space. And then the linear representation acts on latent space. The advantage of this decomposition is that we can reuse our previous method ligand on the latent space because once the symmetry transformation becomes linear, it is exactly the same as our previous task setup. So the problem is reduced to jointly training such an autoencoder that maps the data to a latent space with linear symmetries and then applying our previous method ligand on this latent space equipped with linear symmetry. Yeah, so to have a closer look, we first have the data mapped, fed into an encoder, which maps it to a latent vector. And then the symmetry generator generates some linear symmetry transformations by matrix vector multiplication in the latent space. And then the transformed latent vector is fed into the decoder to finally obtain the transformed sample in the input space. And we have a theorem that roughly saying that this decomposition can universally approximate group actions of compactly groups under some conditions about the group action. And also, we have this theorem saying that the group action is valid if we have the following two conditions. So the previous theorem says that it is possible to do this. And the current page is saying that how we should do this, what kind of condition we should enforce in order to learn a correct group action rather than some random group actions. So first, we need to have perfect reconstruction. And this is quite easy to understand. It's pretty much similar to any autoencoder training. So we just include an reconstruction loss to ensure that the encoder and decoder are approximately the inverse of each other. And the second one is called invariant latent support. This means that if we take all of the support of the input data distribution and map it to the latent space with the encoder, then we have latent support on the latent space of the data distribution. And invariance is saying that this latent support, that is the blue region, the blue circle on the right-hand side, should be invariant under all the possible group transformations. So here in the visualization, we can see that because the latent support is a circle, it is invariant under rotation. Like if you rotate a circle by any degree, then it should still be a circle. So under these two conditions, we can conclude that the group action is indeed valid and match the symmetry of the system. And to enforce the second condition here, we just reuse our previous objective of GAN, saying that the distribution, the transformed distribution in the latent space should have approximately the same support as the input as the original data distribution in the latent space. So yeah, this is our extension to the first method ligand, which basically discovers linear symmetry in the latent space. So again, let's look at some examples of such latent symmetry discovery. And I'm reusing this example of reaction diffusion system from the previous slides. And here, the input is a solution to the PDE discretized on the 100 by 100 grid. And the function here, whose symmetry we want to discover, is the time stepping or the prediction function that takes the current state xt to the next state xt plus 1. And we managed to find this roughly circular 2D latent space which is approximately equivariant to the 2D rotation transformations. And this video shows how we map the original high-dimensional observations to the 2D latent space, and how the group action is transforming both the high-dimensional input samples and the low-dimensional 2D vectors. And we can see that in the latent space, roughly, it is just the rotation transformations. And in the input space, it is yielding the equally valid evolution dynamics of this lambda omega reaction diffusion system. And we also mentioned that apart from high dimensionality, nonlinear symmetry can also arise from the nonlinearity of the underlying dynamical system. So we also included two examples here. First one is nonlinear pendulum, and the second one is the Lockable-Terra equations, describing the relationship between predator and prey populations. So on the first column, we can see that the original trajectories are highly nonlinear, thus preventing any linear symmetries from existing. But then we can map it to some latent symmetries that look like an ellipse or a circle. And in this case, linear symmetry is possible. Basically, it's just the rotation up to certain different scalings in 2 dimensions. And if we apply the whole process of Laligan, we can see that the transform distributions, the transform trajectories on the third column approximately match the original trajectories, meaning that these are approximately the correct symmetry. But if we just apply our previous method, Ligan, to discover linear symmetry, then it will mess things up. So yeah, right now we have introduced our methods for discovering symmetries. But then the question is, how should we use these discover symmetries in downstream tasks to actually do something in terms of machine learning prediction? So then comes our third piece of work called symmetry-informed equation discovery. So here, I think the problem setup is kind of similar to what FirstPrinciples has been doing. It is similar to the problem of symbolic regression. But here we are specifically interested in discovering first-order ODEs rather than general algebraic equations. So here the discovery target is these equations, dot x equals h of x, where dot x means the first-order time derivative, and h is the function we are trying to discover in a symbolic form. And the data set here is just the trajectories of from the ODE systems. So the I here denotes the index of different trajectories, and 0 to t are just the time steps. And the previous examples of nonlinear pendulums and the Lockable-Terra systems are just 2 examples of this ODE discovery setup. And the symmetry we consider here is the flow map equivariance, as we also mentioned previously. So basically, if we have this flow map f, which predicts the future time step from the current time step, and if we know the equivariance of such flow map function, then we can use it to construct an equivariant equation model to do this symbolic discovery. And we have as you can see, we have a whole pipeline depending on whether we know the symmetry beforehand or not, and whether the symmetry is linear or nonlinear. We have different ways of handling things. But in this talk, I want to introduce you to the, I think, the most exciting part to me in this work, which is equivariant SINDI. That is hard-coding these equivariance constraints into the SINDI equation discovery model. So as we mentioned before, we have this discovery target, the first order ODEs in this form, and SINDI, or sparse regression, constructs the H function here as a linear combination of some predefined functional terms. So this is the model assumption from SINDI. So it decomposes H into multiplication W times theta x, where W is the trainable parameters and theta is predefined function libraries. To make this more clear, we can look at the following example. For example, we have two variables in the phase space, and we let the function library contain the monomials of these two variables, x and y, up to the degree 2. So it has it is a six-dimensional vector from 1 to the constant term 1 to the linear term x and y to the three quadratic terms. And in this case, the W here, the trainable parameter, is just this 2×6 matrix, which linearly combines these different functional terms to obtain the time derivative prediction. And to incorporate our symmetry constraint into this system, we make use of the following proposition, basically saying that if we have some knowledge about symmetry, which can either be pre-specified or discovered from our previous method, then it is translated to a linear constraint highlighted in the red box here on the trainable parameter W. So if we look at this formula closely, you can see that it is just a combination of some linear systems, and we can use some standard linear algebraic technique to solve this linear system of equations. So here, I have actually listed how we approach solving this constraint as a linear system, but I don't want to get into too much details about mathematics, just to conclude that, this is something we can solve simply by applying a singular value decomposition of the constraint matrix, and finally obtain the symmetry subspace of W as the form on the bottom right. So here, if we vectorize W, the trainable parameter, into a single vector, then it can be represented as Q times beta, where Q is the pre-computed symmetry basis, and beta becomes the new trainable parameter. And in this case, we just have to optimize for beta and fix Q, and beta is guaranteed to be much fewer dimensional than the original weight matrix, thereby making the entire problem of equation discovery simpler. So again, let's look at some examples of the equation, their symmetry, and the pre-computed equivariant basis here. So for the first equation, we have this damped oscillator. The symmetry of this oscillator can be discovered to be the rotation symmetry. Here we represent it in a slightly different form than the rotation matrix. It is in the vector field format, but here the V here on the first row is actually telling us that this system is symmetric to a rotation transformation in the 2D space. And in this case, we can compute the equivariant basis as the two elements shown on the right-hand side. So here we have two 2×6 matrices, and if we view them as some basis of the vector space, then we can conclude that the weight matrix of the Cindy parameters must lie within the span of these two elements in order for the system to be symmetric to such 2D rotation symmetry. And similarly, for the second equation, which represents some kind of growth in the two-dimensional phase space, it has a scaling symmetry denoted by this vector field 2 times x1 times partial 1 plus x2 times partial 2. We can also compute its equivariant basis. And here, because each equivariant basis only has one single non-zero element, we are combining three bases into one visualization, where each colored block represents a single equivariant basis. And again, if the weight matrix of Cindy is lying within the span of these three basis vectors, then it is guaranteed to have this scaling symmetry. And similarly, we also have an example with much higher dimensional phase space and a much more complex equivariant basis. But in this case, we managed to reduce the 60-dimensional or 4×15-dimensional parameter space to a 34-dimensional space spanned by the 34 basis elements visualized on the right-hand side. And we can clearly see the advantage of this equivariant approach of sparse regression. And if we look at the success probability of the proposed method in some systems, including the oscillator, the growth, and the SEIR dynamics describing the spread of pandemics, we can clearly see that the success probability of finding the correct equation from our method, equivariant SINDI constraint, where C standing for constraints, is much higher than the base method, including the base SINDI sparse regression approach, the weak SINDI variant, and also the GP and decode here, which stands for some approach using genetic programming. And we also show that this method can also be applied to discover latent space equations. So similar to our setup in latent ligand, for those high dimensional data like this 100 by 100 image, it is not possible to have an ODE of 10,000 variables in the input space. Instead, we want a much lower dimensional and much more interpretable latent space to express our equations within. Therefore, we used an autoencoder to map the input data to the latent space and then discover the equation H in this two-dimensional latent space. And here we adopted three approaches. The first one, SINDI-AE, SINDI autoencoder, is the baseline approach. And the second one, La Ligand plus SINDI, is one of our preliminary experimentations where we basically just use the ligand to learn a latent space and then apply SINDI on the latent space as two separate steps. And eventually we have the third method, which we call equivariant SINDI autoencoder, that jointly learns a latent space that is jointly symmetric and has a desirable equation for the dynamics. And we can see that for both variants of our method, the prediction error from the discovered equation on this reaction diffusion system is much lower than the vanilla SINDI autoencoder. And if we have a more fine-grained comparison, we can conclude that our final approach, equivariant SINDI autoencoder, is slightly better than simply combining latent ligand and SINDI as two separate steps. And the conclusion here is that if we have both equivariant model and data represented by the approach of equivariant SINDI autoencoder, it is slightly better than a non-equivariant model on the equivariant latent space. That is non-equivariant model plus equivariant data. And eventually, both of them are much better than non-equivariant model and non-equivariant data represented by the baseline SINDI autoencoder approach. And we do note that there are some limitations of this approach, and there are some possible extensions. So first, we only consider the time-independent symmetries in this method, and it can be generalized to general Lie symmetry. And also, we only consider the ODEs, or ordinary differential equations, in the sparse regression form, but it can also be generalized to general differential equations, including partial derivatives, higher order derivatives, and also implicit function as the symbolic formula. So we actually have a follow-up work on this, but it is in the preprint version. I also included it in the slide, but due to time constraints, I'm not going to cover it in today's talk. But if anyone has follow-up question, I will be happy to answer them. So to summarize, we have introduced how we discover symmetry and how to incorporate the discovered symmetry as linear constraints in sparse regression and generally help equation discovery. And the second point here is actually summarizing the preprint work that I skipped, but yeah, I'm also putting it here. But in general, if we zoom out a little bit and look at the full picture of AI for scientific discovery, whether it is for discovering symmetries or discovering governing equations, there are still some challenges. And first, the current discovery methods are often only capable of discovering general governing laws without having a fine-grained and task-aware understanding. For example, our existing methods for symmetry discovery are designed to learn global symmetry groups. However, symmetry may only hold for some input X and group element G in the subsets of entire space. So we have, to some degree, introduced this notion of local symmetry and formulated this discovery problem in a recent paper, but there are still quite a few limitations and quite a lot to explore. And another challenge, which I think is more imperative, is that current methods, including ours, often heavily rely on human-in-the-loop for a full data-to-law pipeline. And these manually designed discovery pipelines require case-to-case effort, and they may not generalize to relevant scenarios. For example, we have this whole flowchart in the framework of symmetry-informed equation discovery, which took me like weeks to develop and yet did not work beyond specific cases it was designed for, that is ODE discovery and the time-independent symmetry, as we have just mentioned. So to address the second challenge that the current discovery methods heavily rely on human-designed pipelines, I'm envisioning a large language model for agent for scientific law discovery. So I think this is this may be similar to what you have been doing at FirstPrinciples, but from a more specific motivation. So we argue that LLM has shown extensive domain knowledge and reasoning abilities, which can be very helpful in this task. And previously, the AI discovery models just start from data to discover a specific governing law, such as symmetry or differential equations or some other property like integrability and conservation addressed by not my work, but other related work in this field. This is cool, but I would say that individual topics tend to be less enlightening than the connections between them. So we also introduced symmetry-informed differential equation discovery in this new arrow. However, this is only one of the many possible connections between these laws and theorems. And instead of relying on human domain experts to enumerate all of these routes from one physical property to another, I hope that we can use an LLM's rich domain knowledge and reasoning abilities to effectively exploit these connections in scientific discovery. So the language model will decide the path it takes in this interconnected graph of theories. For example, it can discover the symmetry of a PDE from data and then analyze the group structure to see whether the equation is integrable. Or it can start from learning a conserved quantity throughout time and then use Noether theorem to derive the corresponding continuous symmetry and eventually use this as a constraint and try to find out the exact governing equation. And the important thing is, once we have provided the LLM with necessary tools for heavy and domain-specific computations, we do not have to worry too much about designing specialized discovery pipelines for specific scenarios. For example, we don't have to, write 12 papers on exploiting these pairwise connections in the figure, as tempting as it might sound. So generally, I'm envisioning this, designing this LLM agent so we can run the full discovery pipeline following natural language instructions. And then the agent can call existing methods like the methods I just introduced for symmetry discovery and symmetry-informed equation discovery as tools for domain-specific computations. And this closes the entire loop of AI for scientific discovery and can be regarded as the ultimate product along this line of research. And this is the end of the presentation. And these works are done by with the help from my advisor, Professor Rose Yu, and my wonderful collaborators, Manu, Robin, and Nima.